Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right, hello everybody. Welcome to another episode of Ask Us Anything about Electrochemistry. I'm Dr. Alex Paroff. My colleague Neil is out today. This is it's the holiday season, so I'm anticipating that there may not be that many people asking too many electrochemistry questions. Most people are taking a break from research, especially in the U.S. for Christmas and New Year's. Hanukkah is also Hanukkah and winter solstice are also recently happening and are continuing to happen. But with that being said, we may have a short live stream, but we may have a longer one, depending on how many questions we get. So let's just jump right to it. Also, for those of you who are returning, I'm trying to slowly but surely upgrade our studio setup for the live stream. So I actually have a green screen with and we may change the background in the future. But please type your questions into the chat. I just want to make sure that, and then I'll try to get to them as soon as possible. All right, there was a question previously that was put on our YouTube channel from Lino Sacco. Lino says, Merry Christmas. What do you think about single frequency impedance to monitor the resistance of a solution? And how do you interpret C prime, C double prime plot in Faradaic or non-Faradaic EIS? This is a great question. So Lino, first off, thank you so much for your question. Let's talk a little bit about that. So let's talk about the first part, which is using the single frequency to monitor the resistance in solution. So I'm just going to pull up just our good old-fashioned screen here. I just want to make sure everything is displayed, and I'm going to minimize your question just for a minute. So typically, when we're doing EIS, and usually when we're trying to monitor things like the solution resistance, imagine, I'm imagining we have, say, a kind of planar disk electrode, something like this, and it's submerged in the solution. Or actually, let's type it let's draw it the other way. We'll draw it so the electrode goes down, and then we have a kind of a planar disk electrode. That's like our working electrode, and then it's in a solution, and then we have like a reference electrode and a counter. Well, we have a counter, and then we'll have a reference, which looks a little bit like this. This is ref, and this is counter. I don't draw as nicely as Neil does. And all of this is submerged in some electrolyte solution. The counter electrode is a platinum wire. The reference electrode is something like silver chloride with a little frit inside. And when we model this kind of system with EIS, we tend to model it as a resistor called RU. That's in series with a parallel circuit of a and so and this is usually something like CDL, and this is RCT, charge distance. Now, generally speaking, what we're looking at, what we're interested in, is this RU. Looks a little bit like a W, but it's RU. We're trying to monitor the solution resistance. Typically, when you're doing EIS, when you have a very high frequency, omega, here, when this is very high or approaches infinity, the impedance of your system, Z, tends to be equal to Ru. So that is one of the powerful things about impedance, is the fact that we know from, if we modeled this electrochemical circuit, this sometimes called a Randall circuit. Randall's actually has a Warburg impedance here, but if we just if we figure out what the impedance of this system is, and actually I think I can even do it by memory, that the impedance is equal to Ru plus, I think it's RCT over 1 plus J omega. I think it's RCT CDL. Something along these lines. There may not be a. I think there is an RCT here, and I'm sorry if this is a little bit hard. Let me to read. But this is the general expression of the impedance for this circuit. And if you're curious about how I got that, I'm happy to go over it with you. But this impedance, usually when omega here goes to infinity, then we have a number over infinity, which is 0. And that's how we get the expression that the impedance at high frequency is equal to Ru. So the idea is when you pick a very high frequency, such as 1 megahertz, or even higher, but usually 1 megahertz is sufficient. Even like a 10 to 100 kilohertz, it's sufficiently high that your impedance is effectively equal to this Ru. You don't even have to be at infinity. It can be 1 megahertz, 100 kilohertz, even 10 kilohertz in some instances is sufficiently high enough that the impedance you get is equal to the solution resistance. So that means, in principle, you can just pick one frequency and get the solution resistance, and that's a good way to monitor the solution resistance as it changes over time. Now, one thing to note, and I'll actually just make a new tab, that if you're doing this, go back to review. And I may kind of screw this up a little bit, but if you look at the Bode plot, right? So I want to put a Bode plot up. So the Bode plot, we have frequency, omega. You have the it's a big Z there. You have the impedance magnitude, and then you have the phase angle. Usually the phase angle is something like 0, and then you have positive 90, and then you have like negative 90. I should put this 90 on the other side for consistency. So this is positive 90. And this is the phase angle. And usually Bode plots, the red, I think it's a red, maybe something like the impedance, and there's just the impedance magnitude. Maybe it looks like this. And then in our it's a little thicker. Maybe it looks something like this, or something along these lines. I'm not super great at this. But one thing that I want to draw to your attention, specifically if you're going to pick a frequency, you want to pick a frequency where the phase angle is 0. So when you pick a frequency to use for continuous monitoring, you want to ideally pick a high frequency where, this is the high frequency, so high frequency is this way, low frequency is this way. You want to pick a frequency where the phase is 0. If the phase is not 0, that implies that you have some capacitive or inductive processes that are also occurring, and your system does not fully represent just this circuit. Because if it was just this circuit, high frequency, you wouldn't have any, your capacitance values would be very, very low, or it wouldn't contribute. So, so my suggestion to a certain degree is yes, you can use a single frequency. I might use a few frequencies, but generally speaking, you can, and you should pick one where the Bode plot, and I should write this down here. This is Bode, a Bode plot. That's not, I am not drawing very well, but I also don't have as much space because I've overcrowded my desk here. So this is a Bode plot. Look at frequencies that are in this region. You wouldn't want to pick this guy. You wouldn't want to pick him because you wouldn't want to pick one megahertz, for example, if this is 1 megahertz. You wouldn't want to pick that one because you actually have some cable inductance, the way I've drawn it. You have some kind of cable inductance, you have some artifacts that are contributing to your signal. So I would pick something where you have close to or near 0 phase angle as the frequency, and that's and it's high frequency, and that would be most representative of the solution resistance. So I hope that was helpful. I'm going to delete this, and we'll get on to the next question. But if you have, if you want, further clarification, if you will, on that question, please let me know. And I'll try to answer it as best as I can. All right, so the next question from Ramsa. Ramsa asks, how luggin capillary actually reduces IR drop when it is still placed far away from the working electrode? This is a very good question. Let's talk a little bit about and specifically, how does the reference kind of measure, how does the position affect the IR drop? That might be very helpful, Ramsa, in actually answering the question how the luggin capillary actually reduces the IR drop. So let's go back. And all right, so if I'm going to draw what I would describe as an equivalent circuit diagram, sort of say. Let's say my working electrode. Actually, let me do something else. I have talked about this in other other talks about this very subject. So give me 1 second. I'm going to find a slide, or even some slides, where I talk about this. Let's see. Make sure. No, it's not this one. So give me a minute. Give me 1 minute. Okay. All right. Okay, I found it. Thank you for waiting. I hope that you continue to wait. All right, so I'm gonna hide this. So this is from a presentation I had. I was talking about how a potentiostat works. So imagine, if you will, that these are that you have a working electrode, you have a counter electrode, you have a reference electrode. Now, in a solution, you can actually model parts of the electrochemical system as circuit elements connected to each other between the electrodes. These are kind of what we describe as like the compensated resistance is solution resistance between the counter and the reference electrode. We have this kind of RU uncompensated solution resistance between the reference and working electrode. That's what we're going to be kind of discussing, and we discussed a little bit in the previous question. And then the electrical double layer capacitance and the charge transfer resistance are modeled as this capacitor resistor in parallel. In parallel. So this solution resistance, this RU here, is kind of the cause of problems, and we want to minimize it. Now, generally speaking, we kind of minimize it by doing some physical things. So to do this, we minimize the IR drop by, say, increasing the supporting electrolyte concentration, minimizing the actual solution resistance. We also can minimize the current by, say, making the working electrode smaller. The IR drop represents a current times the resistance, which is a voltage drop in the applied potential. And so let me actually just kind of go back to kind of describe this a little bit further. Going back to this kind of diagram, what we ultimately want to do as scientists is we want to measure this. I want to know what the potential is across the electrode, the working electrode interface. And I also want to know when I apply a voltage to my working electrode, I want to apply it across just this interface. But the reality is that it's often that we have this solution resistance that is in series with our working electrode interface. So both the measured potential as well as the applied potential is kind of affected by this RU. Now, this is actually part of a class that I've taught about how potentiostats work and IR compensation, and so we want to minimize this RU. What RU does oftentimes, and in this example, is if it was, say, 300 ohms, and we apply 1 volt, and I'm trying to determine what is the potential applied across the working electrode interface, we could do some math, and we can determine that 0.3 volts is consumed, if you will, by the solution resistance. When we apply plus 1 volt, we only effectively apply 0.7 volts to our working electrode surface. So a luggin capillary, ultimately I will get back to your kind of initial question about the luggin capillary. The luggin capillary is a way that we effectively decrease the distance between the working and reference electrode, a way of minimizing that solution resistance effectively. If I have a very large distance between the working and reference electrode, my IR drop increases because my solution resistance increases. So that's effectively what the luggin capillary is supposed to do. And normally, let me share let me just create a blank here. Normally, and I'll just erase this. Normally, when you have an electrochemical cell, and you say have a reference electrode here, so this is your reference. Put some salt around it. This is ref. This is counter. And then we have working. And we'll just have working here as like a little thing here. Now, a luggin capillary, and this is all in solution. A luggin capillary is effectively an extra tube that does this. It creates a little opening or a hole, and in a way, it guides the sensing point of the reference electrode. It's supposed to create a small distance between the working and reference electrode to minimize the IR drop. Now, if the luggin capillary is like over here, for example, if it's not close to the working electrode, then it's not going to work. It does not minimize the solution resistance. If the distance between the working and reference electrode will play a role in the IR drop. This is a function of the distance between the sensing point, because there's effectively like a field between the counter and the working electrode. Remember, the IR drop, the I in IR drop comes from current flowing between the counter and working electrode. The reference electrode is placed between, kind of within that field, and any current that passes between these two that hits some solution resistance results in a voltage drop that's measured at the working electrode. So if the luggin capillary is pointed in the wrong direction, or still has a large distance between the working and reference, then your IR drop will still exist effectively. So so hopefully that helps. The luggin capillary, Ramsa, will not actually work correctly at reducing IR drop if it's placed far away from the working electrode. Hopefully it's at least closer. The reference, it makes the reference electrode sensing position, that FRIT, closer to the working electrode, but ultimately it might not. And if it doesn't do that, then it will not improve the IR drop. Neil does not like luggin capillaries because he doesn't like the kind of sense of, how is this thing actually minimizing solution resistance or stuff like that. But yeah, ideally that's how it works. Okay. There were some questions from earlier. I do want to. Oh, actually, sorry. I forgot. Lino actually had a second question that I forgot to answer. So, Lino, I apologize if I didn't get to this. That I didn't get to this earlier. Lino asks, how do you interpret C prime C double prime plots in a Faradaic or non-Faradaic EIS? So C prime C double prime plots are basically Nyquist plots. The double prime refers to the imaginary impedance, and the prime refers to the real impedance. And so now interpretation, I will tell you this. I don't know if I can say a lot because there is quite a bit. There's actually a lot of information in the interpretation of Nyquist plots. So actually, I'll go by the way you've described it. And I don't know if I usually think of this as like C double prime is negative imaginary. So I'm also just going to put equal to negative Z imaginary. This may or may not be correct because I don't know if Z prime is actually equal to negative imaginary. But I'm just going to kind of say it this way. Z prime is equal to Z real. And sometimes you get these, you get these semicircles. Maybe you get two semicircles, and then maybe you get like a long Warburg tail. Sometimes you have these curls, these inductive loops that can occur as well. And so the interpretation of EIS data is in and of itself a very big and long topic. And I would actually perhaps recommend listening to one of our webinars actually on it. So on the Pine Research YouTube channel, we have a webinars playlist. There are several EIS webinars that you can listen to if you're a Tier 2 member, and it goes into more details about impedance spectroscopy as well as interpretation and plotting conventions. But I can at least tell you a little bit to kind of get you started. Typically, in general, very generally speaking, every semicircle here is representative of of kind of an RC circuit. Potentially, it doesn't always kind of have to be, but generally, when you have these what we sometimes call capacitive loops, or just semicircles, it's indicative of a charge transfer, sometimes a charge transfer process. We can model the electrode surface here, but there's a time constant associated with these, which means that there's an electrochemical process or an interface, if you will, that is in your electrochemical solution. When you have two of them, you end up getting, this may be this guy right here. And the size of these semicircles are related to the kind of the time constant, if you will. And actually what would be better for me to do is I will try my best to simulate some of these things using our circuit simulation software. So hopefully you're all seeing this. this is our circuit simulation, and I'm just gonna pick. Oops. I need to continue sharing. Sorry, I hit stop share instead. Let me hide this for a minute, and then I'm going to share. This is our software, and in this I just picked a simple two RC circuits, and actually I should add a second thing. But what I can do is I'm gonna keep those around, but if I kind of mess around a little bit with the sizes of these as well as the magnitude of these, make this guy here, this guy small. Let's see, that's RQ2. Let's adjust R2 a little bit. And I don't actually mess with this. Oh, wait, here we go. That's R2. Yeah, there we go. So I can have, yeah, I can't see all of the R's that are here. But sometimes you can have like two semicircular processes, if you will, in the Nyquist plot. And those correspond in some ways to two charge transfer processes. I should be adjusting these a little bit more. Basically, not this one. I think if I went to a higher megahertz, that actually wouldn't do anything. Oh, no, did not want that to be here. Get that back. There we go. So you may end up seeing something like you'll have these two semicircles, and I didn't add a Warburg kind of constant here, but sometimes you may see something. I'll just kind of simulate it, if you will. Let's see. Nope, that's not it. Oh, I'm not doing very well. Yeah. So if I had you can also sometimes get these 45-degree angles associated with what we call Warburg impedance, but that's not what I want to demonstrate to you right now. I'm not doing a very good job of this. Neil is much better at driving than I am. Let me simulate this. But when you have two charge transfer processes, you end up getting these two kind of semicircular features. And if you have more of these RC charge transfer processes occurring, you'll tend to have other semicircles. Sometimes the value of those semicircles will change and adjust. You can even have two semicircular things that kind of form one big semicircle, but even though they're two different processes. So that's just a way of observing, hey, when I have two processes, I may actually have multiple things happening. Let me see if I can't add, let's see, we don't have a Warburg system. Oh, well, actually, this system here is for Warburg, or can be used for Warburg if I make alpha 0.5. And then if I change this here, make that like so. And there we go. So sometimes you can have what's known as Warburg impedance, which is this kind of 45-degree line that'll come out. Again, I'm just talking about things that you'll tend to observe in electrochemical systems. You'll have a charge transfer process here. You may have some solution resistance that manifests itself as kind of this line here. If you have more resistance, kind of the x-axis offset will be here. But that's another way. It's oh, I have one charge transfer process, but it's coupled with a kind of Warburg diffusional tail, if we, as sometimes described. So I know that's kind of a lot, but I wanted to at least answer a little bit about some level of interpretation or thinking about Nyquist plot data. Okay, all right. So Ananth Chem asks, how can exchange current density be determined And what are the common methods used for its measurement? That's a very good question. So let's start, if you will. I'm going to minimize your question for a minute. Let's actually start by looking at just the basic equation for exchange current density, or that contains exchange current density. All right, so this is the Butler-Volmer equation. The exchange current density actually is kind of a normalization factor of FA and K. Actually, an N, I believe, is also in here as well. But FAK all multiplied together will give you the exchange current density. There may actually even be a concentration, but the exchange current density is related to like the heterogeneous rate constant, A and F. So, and the Butler-Volmer equation, loosely speaking, tells you that the net current of your electrochemical reaction is equal to a bunch of constants, including the heterogeneous rate constant. And then it's multiplied by the concentration of your oxidized and reduced species at the electrode surface based on this equation here, where OX plus an electron gives you red. And the concentration of your oxidized species that's undergoing the reduction reaction is equal to E raised to the minus, parentheses 1 minus alpha times NF over RT times E minus E naught, which is basically the overpotential, the potential beyond the thermodynamic minimum to drive the reaction to go forward, and minus the concentration of your reduced species raised to the times E raised to the alpha NF over RT, again times the overpotential. So ultimately, when you want to get the exchange current density, you're really looking for, you're kind of looking for this term here, ultimately. But you're more importantly, to think kind of fundamentally, what is the exchange current density? It's kind of the current that when you're at E naught, sort of say like if the potential is E naught in this case, right, then these terms basically go to 0, right? So this term gets multiplied by 0. E to the minus 1 is just, or E to the 1 really is just, or E to the 0 is 1. E to the 0 is 1. You have the difference in the concentration of your species multiplied by FAK. Now, usually the way the exchange current density is determined is through the Tafel equation. And let me just make sure that I'm kind of, I don't want to skip other people's questions as they come up. Usually it's done through the Tafel equation. This is another representation of where I0 is the exchange current density. It's probably a better way. And eta is the overpotential. So Tafel equations are typically used to extrapolate the exchange current density. And again, the exchange current density is actually really a measure of how quickly a reaction occurs, how facile, how easy it is for a reaction to occur. Now, if I remember how to do this correctly, you want to first off generate a Tafel plot, and there are numerous ways of kind of plotting or looking at Tafel plots. Sometimes they have the current here, sometimes or the log of the current here. Sometimes they have the log of the current here. If I plot the overpotential here, let's say I just have voltage here, eta, and then I have the log of my current, or log of the current. Well, it doesn't even have to be this, but yeah, you can have the log of the current divided by the exchange current density. But if it's the log of the current, typically these Tafel plots tend to look a little bit like this. And this is 0. So this is 0 over potential. And they go out like so. Sorry, it's supposed to be a smooth line. Now, typically, within this region here, you're not getting. Actually, I'm trying to think if there's a good or an easy way to kind of think about or describe kind of the relationship between overpotential and the exchange current density. Usually, what happens is once you're able to create a Tafel plot, you're able to kind of get the Tafel slope. So even though these lines are curved, you want to omit data in this region because usually, if we go back to the Butler-Volmer expression, if we are in one potential regime, so let's say this value is very high, we're at a very, very high potential here. Well, this is negative. So this side of the reaction actually dominates. And even though this sign is negative, it just means you're getting like a negative current instead of a positive current. But as you move away in either direction of the overpotential, you tend to get more of a straight line. I think I've drawn it a little bit curved. But when you do that and you're beyond the limits where just one side dominates, you end up getting these kinds of Tafel, these two sides of the Tafel plot. And I believe where these plots kind of intersect allows you to get some information about the exchange current density. This is kind of like where your I0 is, which I know isn't exactly a very easy or good thing to do. But ideally, you can even look at this here. And when you're able to relate the two Tafel slopes in this equation here, you'll be able to extrapolate, because these things will be different. They won't be equal to each other, but they'll be different, and you'll be able to extrapolate an exchange current density from it. I'm sorry I don't have a quick, easy answer for it. This is not a calculation that I do very often, but the exchange current density is determined using the Tafel equation, and a Tafel plot is usually made using a rotating disk electrode experiment. Specifically, and here's another thing that's important about using Tafel and exchange current densities is this value here, this heterogeneous rate constant. If you have you need to have slow electron transfer rates and very slow kinetics rates for Butler-Volmer and Tafel to work, because for this voltage difference to be sufficiently big enough, you can't use data that's here. And the best way to actually measure this is with a rotating disk electrode experiment, which tends to look something like this, where you have current and voltage. Well, if you have a very small voltage range where you're collecting data from, which tends to be the case with fast electron transfer kinetic systems, you won't be able to actually get good data to do a Kurecki-Lević analysis, which allows you to get the current values, the kinetic current values that are needed for this experiment, because you have the voltage here and you have the E naught of your system. So you can create this kind of plot. I'm sorry I'm not being more specific, but I probably, Ananth, I'll probably, I can maybe come back to this later, and then go into a little bit more detail about how to determine the exchange current density. But I would even say a more important thing to do is just determine the heterogeneous rate constant. You don't always have to have the exchange current density. The heterogeneous rate constant is a more general term that is not area specific. Like the heterogeneous rate constant is area specific. The exchange current density is area specific. It's always good to have a term that's like not area specific. So hopefully that's a little bit helpful. I'll think a little bit more about your question and see if I can't provide some more help, if you will, on that. Okay, kind of moving on. We have a question from Bill Clinton. Let's see if I can answer. You've always asked some very good questions. It really gets me to think hard about electrochemistry. What factors determine the rate of electrode deposition in an electrochemical cell with a superconducting electrode? And how does the critical current density vary with temperature and electrolyte composition? Oops. I think I'd have to think about that a little bit more. The rate of electrode deposition. The rate of electrode deposition, I think for any kind of, the rate is usually for any kind of, well, electrode deposition specifically is almost like any other electrochemistry reaction, if you will. Right? It's you have some kind of electron transfer process. So mass transport is going to be a big player in this, because electron transfer by itself is actually pretty fast. But its electron transfer rate is going to be very important. And then mass transport. How much mass can you get to the surface as quickly as possible? So that's usually the thing that determines the rate of, say, or turnover frequency of a reaction. If you want to know a little bit more fundamentally, like what governs the kinetics, like why does electron transfer happen faster for some molecules than other molecules, that usually has to do with like transition state theory and Marcus theory, and the idea that if your oxidized or reduced state is are similar to one another, such that there's not a whole lot of molecular reorientation, then it's very easy for an electron to either move into or out of that state. But I can't talk about a superconducting electrode. I actually don't know enough about superconductivity to really kind of talk about that and what superconductivity is in electrochemistry. I understand it simply as like, okay, you have like almost no resistance, sort of say, for like pushing electrons through. But I don't know what the critical current density is, and how it varies with temperature and electrolyte composition. I think every system will probably be a little bit different, but I think I would need to know exactly what you mean by critical current density. Because there's a current density. What the critical one is, I don't know if that's supposed to be the maximum one. And I feel like with every system, like temperature and electrolyte composition, it would be a little bit different. So, sorry, Bill, I don't have too much more information beyond that, but that's hopefully, and then, what potential all these reactions are happening. I don't know how a superconducting electrode, how that works. So I'm sorry, Bill. All right, we have a question from LinkedIn from Francisco. Francisco, thanks us for our time. Always happy to give it. I have a question related with the correct way to determine the half-wave potential in RDE measurements. It's a good question. Okay, so what is the half-wave potential? So let me see. So let me see if I can let me talk about this for a little bit. So let me move away from this. So when you're doing an RDE experiment, you have a voltage and you have a current. And let me minimize your question so you can see all this. So this is your RDE, and let's say it's this is 0, and then this is your mass transport limiting current. Let's see. So you start here, and then you go something like this. And this very, very, and you're basically trying to figure out like if this is A plus an electron in equilibrium with B, your question is, what's the E naught? What's the half wave potential? E naught or E1 half, I guess E1 half if you're not under standard conditions.
All right, so generally speaking, we think that, like, well, I can kind of eyeball it. It's like, it's right here. We want to get this voltage, right? That's what we want to get. So some people, I think, honestly kind of eyeball what the half-wave potential is, and that's not terrible. But a kind of better approach, because you can have RDEs that are kind of tilted. You also have RDEs that are kind of tilted, and when you have RDEs that are kind of tilted, you know, it makes it kind of hard, kind of questionable, if you will. You know, what point is it? So this is what we do at Pine, what we kind of suggest, or at least what I'm suggesting. And maybe I'm wrong. Maybe I'm wrong with this. So let me erase. Oops, I didn't want to erase that. I don't want to move that either. Okay. Let's just erase this. So what I would do is, if I have my data, and I'm going to use red to kind of illustrate this, is I would use a baseline tool. Going to use a baseline tool. So this is a baseline, because this is baseline. Because this is maybe slightly sloped. And then I'm going to use a baseline tool here. This is also baseline. So I have these two baseline tools. And what I'm going to do is I'm going to try to figure out at what point, at what voltage, is the distance from here to here equal to the distance from here to here. So these two guys need to be equal to each other. And to do that, you kind of need to, there's a little bit of eyeballing, but you know, if you're up here, you can clearly see that this is too big or this is too small, and you can get current values for these two differences. But when these two are equal to each other, then the voltage at this point, at this data point, is the E naught, or the E1 half, the half-wave potential under non-standard conditions. So I use two baseline tools, and then I look at the current where both of these currents are equal to each other, and that is how I determine what the half-wave potential is. Of course, you want to make sure you're corrected for IR compensation and things of that, but that is how that's how I'd go about it. Francisco, hopefully. Hey, Chris, good to see you. Good morning, maybe afternoon, but thanks for sliding in, as always. Neil is out. Hope you guys are all hopefully all of you are enjoying your holidays. I'm glad that you're all asking good electrochemistry questions. All right, so just moving on again. If I haven't provided an adequate answer for some people, and I know I haven't. I know for like exchange current density, I need to have a better description of that. But I'll hopefully maybe be able to come back to some of these questions later as I try to answer as many as I can. Dokukan. Again, sorry if I'm mispronouncing names. Is electrical engineering student here, trying to design a circuit to feed a PEM electrolyzer. I would like to ask, does EIS method gives parameters of the equivalent circuit just for a certain voltage range? I would say yes and no. So this is a kind of perhaps a semantic thing. I'm sorry, I have a lot of wires here. I'm kind of tripping over certain things. This is maybe a semantic thing. So EIS by itself doesn't give you an equivalent circuit diagram, right? You have to kind of guess what the equivalent circuit diagram is. But under different potential conditions, your circuit diagram can effectively change, if that kind of makes sense. I've actually been reading a lot into this. You can imagine under one potential, a certain reaction is occurring, and you can use an equivalent circuit diagram to model that. But at a different potential, there may be multiple electrochemical reactions occurring. You would use a totally different electrochemical equivalent circuit model to model that system. So again, let's just give a very quick example. I'm just going to draw something real simple here. Let me just go to a new slide. Stop deleting everything. If I had, let's say I was doing cyclic voltammetry, for example. This is CV, and I have this, and then I have this, something along those lines. If I do EIS at, this is V1, this is V2, and this is V3. If I do EIS at any of these different voltages, my equivalent circuit model can actually be different for each one. And that in part is because, if I just take a simple Randall's, what I call a Randall circuit, I think it's named, actually, yeah, I'll just do a Randall circuit. There. Has a W here. This works really well here, but I need something else for this one here. I need something like, I got solution resistance, and then I got this, and then I got this. But then I may have another process here. Sorry, drawing off the screen. And similarly, if this process, if I'm over here, this process may have like a very high impedance, like equal to infinity. So if I have an infinitely high impedance that's here, right, because nothing's happening at this voltage, then my circuit reduces to just this. Right? Like, why do I need to put a parallel process with an infinitely high resistor? Everything's going to go through the capacitor. So to answer your question very simply, you absolutely can use, at different voltages, you can use different equivalent circuits depending on what chemistry is occurring. So hopefully that's helpful. Let me know if you want me to, answer that or talk about that in any more detail. All right, so now let's see, kind of moving forward. Let's see. Tommaso Credo, how capacitance change if I use KCl solution with a screen printed electrode, bare, and with a bound antibody-antigen? Should I look at the capacitance frequency plot or real imaginary parts of capacitance? Okay, so the capacitance should certainly change. You have a different structure on the surface in both of those different situations, bare and an antibody-antigen on the surface. So what I would do personally, if I was looking at this capacitance change, I would do one of two things. Pardon me. If you are using EIS, I'd use EIS to determine this, but you can do the same thing with, say, cyclic voltammetry. So, for example, let's go back here. Gonna use my lasso tool and get rid of this. So if you're doing cyclic voltammetry, so you have so this is like SPE. I'm just gonna kind of draw a simplified like SPE, and this is a dot there, and you have a counter here, and then this is another SPE. That is a better drawing because I thought about it a little bit more. And then I have my counter here. Okay, so this, and let's say they're the same size. One of them has your antigen antibody on it. One thing you could very simply do is just do EIS of both of them at the same potential. Looking, oh, sorry, this is supposed to be Z real. So this is Z real. Z real, negative Z I, negative Z I. And it may be the case that, you get something that looks like this, and then, but here you get something that looks like this. And clearly, like, there's a difference between these guys, and then there's a difference in the height, right? The higher, the higher this guy is, not directly, but all of your imaginary impedance comes from changes in capacitance in some ways. Capacitance and resistance, truly. But I would do some circuit modeling, and when you do circuit modeling, again, like the electrodes, you actually, I kind of take this back. Depending on how this is put on, you could have this, but you could also have, you could maybe even for this system, you could have multiple charge transfer processes, because you may have parts of the electrode that are not exposed. Or this one actually, if it's nothing here and you're just looking at your your antigen thing, this may just show up as just like a straight line, because you just have like a resistor and a capacitor in series. There's no charge transfer process. It's only here that you have charge transfer processes that are occurring. But I would model these two systems. That's one way to go about it. It's a little complicated, and you need a potentiostat that can do that. But another thing that you could do, alternatively, and I'm just guessing, I don't know if this will actually work, is you could, again, this is your screen print electrode, and then this has the antibody thing on it. I'm drawing this quickly. You could do CV. You could just do current versus potential and just do a series of like scan rate studies, with each of these being like, you can do like 10 millivolts per second, and then 50 millivolts per second, and maybe 200, 100, 200 millivolts per second. And the current, if it's a box like this, it's capacitive in nature. So you can compare this between your with and without antibody system. This is just black. And look at the difference if you get similar or smaller or bigger capacities. And the current is equal to the capacitance times dV dt, the scan rate. You would then do a linear regression of this. So you would have scan rate. You should have a linear relationship between the scan rate and the current. You should get a straight line. And the slope is equal to the capacitance. And that's another way, that's another method for determining the capacitance of determining the capacitance, say, of your screen printed electrode with and without the antibody. Sorry, I didn't remove this. Sorry, if you have a linear regression here of current versus the scan rate, you should get a straight line, and the slope is equal to their capacitance. So that's another way that you can determine what the capacitance is. EIS is, of course, a bit more, takes a little bit more work, but it's a more accurate, tends to be a little bit more accurate, more sensitive. You also have to pick a sufficient voltage range where your antibody also doesn't like get flung off the electrode surface. So EIS is a little bit better that way. But yeah, hopefully that's helpful. Okay, so let's go to the next one. Sorry if I can't pronounce him. Merry Christmas. Thank you. What do you think about spin of electron influencing electrochemical reactions? It's a good question. So spin, and again, we're talking about kind of the orientation, whether it's like plus 1/2, minus 1/2, the magnetic spin of an electron in an orbital. So, so this is a good question. In some electrochemical reactions, the spin influences the rate of the electrochemical reaction. If you have certain molecules with different orbital orientations, if you will. In the book Understanding Voltammetry, I actually have a really good example of this, and I don't have the book with me right now. But the rate of electron transfer is very much based on, like, okay, the movement of the electron from the electrode to the molecule, or from the molecule to the electrode, is based on, you have to have energy overlap, same energy levels. If it's a homogeneous electron transfer, then it tunnels through the solvent. But electron transfer on the side of the molecule is very much dependent on the orientation of the molecule between its, quote, oxidized and reduced state. Electron transfer typically is, electrons moving is much, much faster than, say, the protons and neutrons, the nucleus of atoms in a molecule. This is just basically the Frank-Condon principle. So they move so much faster. So it's only when a molecule is oriented in the right configuration of the, quote, transition state, where it's like, okay, I am now in the configuration where I can accept an electron. Now I get an electron transfer to move. So if the difference between the oxidized and reduced state is very little molecular movement, so to say, or molecular geometry, electron transfer is very fast. It's very, very easy. Now, if the oxidation and reduction of that molecule involves a change in the spin of the electron, then the electron transfer rate is very, very, very slow. So there are a few molecules, a few atoms where it just so happens that the electron has to do a flip to actually go into the orbital of a molecule. And I'll give you, I guess, a simple example. I'm just kind of somewhat making these up a little bit. Let me delete these last few slides and make a new one. So let's go to. So I don't know. So here's the thing. I don't know enough about the electron on the metal. But generally speaking, if I have orbitals here, just making this up. So I have my here, it's all filled. It's very happy. And then I have this. And so these are kind of like my good bonding orbitals. So this is the HOMO. And this is the LUMO. Then usually if there's an electron in my metal that's like this, it has to undergo like a spin flip to go here, to be here. That is like forbidden, and that makes electron transfer very hard. I need to think a little bit more about like specifically why don't you just take this guy? Why don't you take this guy and do it? That may also happen. But there are instances where the spin orientation of the molecule on the HOMO-LUMO side does play a role. And that may also have to do with like gaining and losing electrons on the side of the molecule here, not necessarily on the side of the electrode. So that can play a role. It absolutely can influence the rate of an electrochemical reaction. Specifically how, I don't completely know. Sorry. Okay, so thank you all for your support. Let me answer. Now it looks like Dokukan has a follow-up question. So thank you so much. So I need to decide which voltage to work at when I evaluate the equivalent circuit parameters for that specific voltage point. Do I need to? So what you will, yes, yeah. So let's kind of share screen and just let's kind of talk a little bit through it, just a little bit. But what you will end up doing is, let's say you have, this is what can happen. It doesn't mean it will happen, but it can happen. And it depends on how complex your system is. If you're working with PEM fuel cells, for example, I don't think that your circuit's going to really change very much. But sometimes different processes can happen. Let's say you have 3 different voltages. At each one of these voltages, you're going to have like a Nyquist plot that may look, like this. Or it may look like this. Or, you may have something that looks like this. You may have, like, literally at these 3 voltages, you're going to get, this is your EIS data. Now, is this, I don't know. I honestly don't know. Probably not. What's actually going to happen, what most likely is going to happen is, you're going to get something that's going to look like this. And then you're going to get something that's going to look maybe like this. And then you're going to get something that's going to look like, I don't know, probably maybe even the same thing. And really, like, the magnitude and the relative ratios of these things, like the circuit may actually be the same, but the values of your circuit elements will be different. That's another possibility. The shape of the impedance data will in some ways govern a little bit. It'll inform you, I should say. It will inform you a little bit if there are changes occurring in your PEM fuel cell, PEM electrolyzer. So, because, well, actually, let me stop sharing. Let me share something. I'm trying to think what's the best thing to show you. But, like, let me at least just show you this one thing quickly. This is from our software. So I'm going to do, let me just do 2 new circuit simulations for you. I'm going to delete these. Hopefully, yes, you can see them. So I'm going to do two circuit simulations. So let me try to share this. Actually, this may be a little bit easier. Okay, share circuit library. Okay, hopefully you can see this. This is the circuit library that we have in our software, and you can see the circuit there. Let me try to make it a little. Well, it doesn't actually change the size very much. So this is the circuit. This is the impedance response, the Nyquist plot. This is the circuit. This is the Nyquist plot. This is the circuit. This is the Nyquist plot. This is the circuit. This is the Nyquist plot, and so on and so forth. Sometimes you'll see, like, some of these look pretty much the same. Like, these two look exactly the same. But some of them will look very different. Like, when you have an inductor, you're going to have inductive loops. If you have something that looks like this, it's going to look like that. So sometimes your circuit is not going to change very much. But sometimes your circuit's going to change a lot, depending on what the voltage is. I do believe that in your PEM electrolyzer, you are not going to see massive differences in the circuit diagram. But you can, depending on the voltages that you pick. So hopefully that will help you in that. Okay, biochemist, I do see your question. I want to answer this question really quickly. There is a section, I don't have a very good book about spin dependence on electron transfer, but this book, and I'm going to share, I'm going to actually just put this book in the chat. Oh, that's huge. This is just a Google search. I don't think that'll actually show up. Okay, it does. So that's the book Understanding Voltammetry there is a section that talks about a particular example of when the spin changes, you get different rates of reaction. That's just an example in the book, but I don't think that there's a book. I don't think there's a book dedicated to spin-dependent electrochemistry. Just my knowledge. I think that most people just, there's just papers. There's just going to be like several papers that either do some level of modeling, I think there may just be some papers that just go into some level of modeling of some spin-dependent electrochemistry. But most of the time, it's just going to be a few papers, a few handfuls. I don't think there's a lot of information about spin-dependent electrochemistry. Okay. All right. So I was able to post that on a few platforms. Okay. All right. Okay. So Biochemist asks, I am a new researcher of Ph.D. Biochemistry. My research is based on CV. I want you to make a video that how to use a CV instrument. Can you please upload any tutorial how to make files, etc. So it's actually kind of funny. I am in the process of making actually a voltammetry webinar series. I know I'm kind of getting ahead of myself. It's something that I've wanted to do for a while. But so I can give you a very simple, right now I have this instrument right here. So I'm going to just minimize your thing. Right now I have this instrument right here. This is a potentiostat. So this potentiostat is capable of doing cyclic voltammetry experiments. It has a cell cable that I currently have connected to a dummy cell. So these leads normally will connect to, these will normally connect to an electrochemical cell. So your electrodes, your working, your counter, your reference electrode, they'll all connect to these leads. And then using the software in your potentiostat, and I'll just show you mine, for example. So this is our Aftermath software. I'm going to delete this. But when you're doing this, you should be able to select an experiment, in this case, cyclic voltammetry. And when you do that, you'll be given several different parameters to explore and need to actually fill out. You need to figure out the segments, just the number of kind of segments, the cycles, if you will. So one segment is just going from like point A to point B, but two segments would be going like from point A to point B back to point A. You have an initial potential where you start off at. You're going to either you're gonna apply a potential, or you're gonna either rise. You're gonna go from a low to a high potential, or you're gonna go from falling high to low potential. You set the upper potential and the lower potential limit, as well as the final potential. And there's a rate with which you scan the voltage. So we have a nice little easy button here that I can do. And if I plug these guys back in, I can just show you a very simple example. I just have a 1 kilo ohm resistor here. And if I get all this together, and let's put, there we go. It's missing one cable. If I just hook this guy up to a 1 kilo ohm resistor, and I perform this experiment, I started at 0 volts. I'm sweeping upwards. I'm going to go to about 1,000 millivolts. And this is just a resistor, so I'm just getting a straight line. Nothing. I'm basically reproducing Ohm's law in this particular case. This is a good way of determining that your potentiostat's working. And normally, if you had some electrochemical system, you would see different curves, you'd see different things, you'd see a bunch of stuff. But right now, I just have a resistor. I don't have a full electrochemical cell and system on me. But just hit the perform button once the parameters are set and your experiment is set up, and you would be good to go. And then you'll actually get this cyclic voltammetry data. You can get other information like the current versus potential, or the current versus time in this case. You can see what your applied potential waveform is. But that's the gist of how to do a cyclic voltammetry experiment. I have videos on doing cyclic voltammetry, but I'd recommend that. Also, if you are based in the U.S., we Pine in 2025, and we haven't updated our website yet, but we host a bunch of workshops with local universities that are around us, and there are these kind of 2 to 3 day fairly intensive workshops on cyclic voltammetry. So if you are interested in that, leave a comment in the video on the YouTube channel, and I can send you information when the time comes. And for anybody else who's interested, we have workshops where people who are interested in learning electrochemistry and cyclic voltammetry, or EIS, we can help. We can help with that. So yeah, that is kind of it. Oh, and then I learned something. I'm currently a PhD in biospintronics. Okay, very cool. I don't know enough about biospintronics. I will say the book, if you look under the kinetics section of the book Understanding Voltammetry, there is a section about understanding electron transfer kinetics. It talks about Marcus theory and stuff like that. There is an example of electron transfer where he talks about how the spin changes. So hopefully that is helpful. Okay. Okay, so I think I've gotten basically most of the questions that we have. I'll wait for some more. There was a question from last week that I wanted to answer from Anuradha. Sorry, again, can't pronounce everybody's name. Hi, I'm doing chronopotentiometry, AST, using an RDE. Is there a maximum voltage limit I should use to avoid damaging the instrument and gold change disk electrode? So, this is a very good question. It's not so much the voltage that can damage your electrode. It's more the current that can damage your electrode. So the current that flows through your working electrode is the thing that's ultimately going to potentially damage your electrochemical system. Now, if you had a very low resistance or a low impedance, a small voltage can generate a lot of current. But similarly, if you had a very high load and you're not getting any current to pass, then you might need a high voltage just for an appreciable amount of current to pass. So this is a kind of a tricky question. Now, a gold change disk electrode, relatively small. Gold is also a fairly generally inert electrode material in the sense that it can oxidize, but it takes very, very large positive potentials to oxidize and damage a gold electrode. Now, I will also make a comment that most instruments are fairly robust, and they have voltage and current limits on them, and they will not surpass the current and the voltage that they're designed to handle. So that being something like our WaveDriver 200 here can take 1 amp of current, one whole amp. But if someone tried to apply more than 1 amp, there are safety precautions, if you will, inside the instrument, things that prevent more than 1 amp from passing through the circuit that would normally damage the instrument. Now, does that mean that you can't damage the instrument? Absolutely not. You can absolutely do things to damage potentiostats, static discharges and frying other things. If you do pass way too much current through your system, through your potentiostat, you can and will damage it. But that being said, I have personally found that in the lab, potentiostats are fairly robust systems. This actually brings me to a very important point that I ran into with a person. So one thing that somebody did, and I'm not going to call out somebody's name or anything like that, but the potentiostat by default actually is in what we would describe as an inactive state. It's disconnected. So you'll notice here it says cell connection disconnected. And when I'm in an experiment, for example, let me actually run this guy again. And then if I go back, let's see if I can, cell state. It actually connects when the, yes, so like status connection type. That's actually kind of interesting. I never noticed that it doesn't actually show you this. But it's connected. When it's done with the experiment, it disconnects. Disconnecting is a way that you're able to, in some cases, protect the instrument from doing stuff that you don't want it to do. I'm going to stop this experiment. But the disconnected state is kind of a good one to be in if you're not in an experiment. And you only want to change that if you want to kind of maintain the electrochemical system. You have a system under study and you want to maintain a load on top of it. So that's kind of a that's kind of a thing. So I think it's hard, not impossible, but it's hard to damage the potentiostat in the instrument, sort of say, in chronopotentiometry. And the ChangeDisk electrode can take a considerable amount of current, but I would only say, in my experience, I think tens of milliamps is a fair bit of current, quite a bit of current for a ChangeDisk gold electrode. If you go beyond that, like 100 milliamps, that's maybe okay. That's really starting to push it. I think 1 amp is a lot of current to pass through a fairly small 5 millimeter disc of gold. So it's the current rather than the voltage that I think is the thing to watch out for. And you may end up damaging other components, not the gold, by having such a high current pass through it. I hope that's helpful and let you know. Okay. Sir, what are my thoughts on modern electrochemistry by Bacchus? I have not read it. I've heard weird things about Bacchus. He has probably since passed away. This is just stuff I've heard from people. It's probably a decent book, but it's funny because it's called Modern Electrochemistry, and like that was a very, very long time ago. So even electrochemistry from then has changed quite a bit, probably. But usually people go to, like, say, read Alan Bard's book, Electrochemical Methods, Fundamentals, Applications. Will Heinemann and Kissinger have a book as well that's very good. Understanding Voltammetry is not a bad book by Compton, but I have not read Modern Electrochemistry by Bacchus, so I can't comment too much on that. So sorry about that. So that is that question. It's good. There's another question that honestly I want to at least mention, but can I suggest a good review article that talks about spectroelectrochemistry? I cannot. I don't know about too many books. There are plenty of papers that go over it, but really, I can talk a little bit about just like the experimental execution of a spectroelectrochemistry experiment, but it's a little challenging. There is a timing. So in spectroelectrochemistry, you're basically doing electrochemistry, and while you do electrochemistry, you shine light, either IR, UV vis, Raman light, and then you collect the backscattered or the transmission mode light from forming a spectrum. And it helps you learn more about the kind of the in this case, it will tell you about the electronic properties of the oxidized or reduced species that you are interrogating. Raman is very good at looking at the vibrational modes, so you can look at changes in the vibrational modes of the oxidized or reduced species. IR similarly does the same thing. And so it's very helpful. It's a very cool and useful experiment. But I don't have a good review article on spectroelectrochemistry. That's something that I probably do need to look at and look into. Most modern electrochemistry books, like Bard and Faulkner, from Electrochemical Methods, Fundamentals, and Applications. And let me find Bill Heinemann's book. Heinemann. History book. Laboratory techniques. Here we go. So I'm just going to share my screen to show you, and this is probably helpful for a lot of people. But this is Laboratory Techniques in Electroanalytical Chemistry by Pete Kissinger and Bill Heinemann, or William Heinemann. This book, this talks about laboratory techniques. So if you want to know more about spectroelectrochemistry and the actual development experimentally of a spectroelectrochemistry experiment, the execution of it, this book is actually very helpful. I found this book to be very helpful in graduate school. For me, it was just a little bit easier to read and more down to earth with experimental considerations, sort of say. And it looks like I purchased this book back in 2011, very, very long time ago. I don't know if I actually have it with me. So, but hopefully that's helpful, or that's at least a good book. But usually a Google search of just general articles is helpful for learning and finding some backup information on electrochemistry. Okay. All right. I think those are the main things that I want to talk about. I'll wait a little bit for if there are any additional questions. I'm sorry if I wasn't able to provide better answers on things like exchange current density. It does require the Tafel plot to really calculate the exchange current density and the rate constant. I also don't know enough about like superconducting electrodes from Bill Clinton. So, but hopefully that's helpful. All right. So there's a lot of so I know we're kind of in the holiday season, so things are naturally very quiet. We may end the live stream a bit early. You can always continue to follow us on YouTube. Write questions in the comments section, not just of this video, but any YouTube video on Pine Research, and we'll be able to look at it and perhaps provide a much more clear and thorough answer during the next live stream. Myself and my colleague Neil should be around for the next live stream, which will be after the new year. But if you decide to take a break from doing some electrochemistry, do enjoy the new year. I continue to think about electrochemistry all the time, no matter what time it is. But anyway, I think this is a good kind of stopping point, and yeah, hopefully you all have a very happy and healthy new year, and you're able to do some good electrochemistry, and I'll talk to you all later.